All right. So greetings, YouTube. This is the second installment of a three-part uh, series of questions that came in. So this is number 7. This question comes from calculus, and it asks us to evaluate the limit using L'Hopital's rule. So we have the limit as x goes to 0 of this expression, but notice if we just try to evaluate the limit directly, if we try to plug in x equals 0, we're going to get an indeterminate form, right? So I'm going to rewrite this using properties of exponents and logs. Okay. So I'm going to rewrite this expression in the following way. This is going to be the same as the limit as x tends to 0. Let's make that arrow a little bit better. X tends to 0 of. Now, if we want to evaluate the exponent, we need to get it out of the exponent. So we can use the property of exponents and logs. This is going to be the same as e to the power of the log of that original expression. 1 plus 2x to the power of negative 3 over x. So when we do this, now we can apply the property of logs where now this exponent can come out and come in front, right? So then we're going to have the limit as x tends to 0 of e to the power of negative 3 over x times the log of 1 plus 2x, okay? So I did a little bit of research and I found that, okay, the limit of an exponential, we can actually do the following. This is going to be the same as e to the power of the limit as x tends to 0 of this thing. 3 by x times the natural log 1 plus 2x, right? Okay. So now let's just focus on the exponent for right now, and we'll come back to this expression. So if we do the limit as x tends to 0, now let's see. I'm going to rewrite that expression in the following way. We're going to have negative 3 times the log 1 plus 2x. I'm going to write it like this, all over x, right? I just combine the two fractions. So now I think we're ready to apply L'Hopital's rule. So basically, L'Hopital, like if we try to, basically what we do is take the derivative of the top, take the derivative of the bottom, and then evaluate the limit. Okay. So then this gives us, so we're going to have the limit as x approaches 0. So let's focus on the derivative at the top. So the derivative at the top, I'm going to use the product rule. I know that's a little bit extra, but I'm just going to use the product rule. So it's going to be the first, which is this guy, the negative 3, times the derivative of the second. So the derivative of log, the derivative of natural log is dx over x, right? So that's going to be d by dx of 1 plus 2x over 1 plus 2x. That's the derivative of natural log, right? First times the derivative of the second, plus the second times the derivative of the first, but the derivative of a constant is 0. So that second term actually goes to 0, so we don't have to include it, right? I'm not going to write it here. And then the derivative of the bottom is just 1. We don't really need to write that either, right? Because the derivative of x is a constant, is 1, right? So now we just need to evaluate that derivative, what you see on the screen now. So then this is going to be, oops, I don't know why I put that there. This is going to be the limit as x tends to 0. Let me see. So the derivative there, derivative of constant is 0. Derivative of 2x is just 2. So that derivative ultimately is 2. Okay. So on top, it looks like we're going to have negative 6 divided by 1 plus 2x. Okay. I feel good about this. So now, if we apply the limit, now if we evaluate the limit, we're going to get 1 plus 0 under the negative 6. And I think we get a result of negative 6. Let me see. Oh, wait. We're not done there. This was just the limit of the top part. We need to go back and apply it to the change that we did. So earlier we had, and actually this equal sign shouldn't be there. So earlier we had e to the limit, e to the power of the limit as x goes to 0 of, let me just copy and paste. That might be a little bit easier. We had all of this, copy, paste. But then we already evaluated this limit, right? So then this is going to be e to the power of -6, right? All right, so then what I'm going to do, I'm going to hop over to my trusty, dusty, rusty calculator. Let's clear this out. Okay. Okay. So now, e to the power of -6 is approximately this number here. So this is approximately equal to 0.002478778. Let's do 8. Let's just do 75. I'm just taking it to a long decimal, right? And let me move this way. Again, e to the -6. E to the -6 is the exact result. And then, so the reason I'm using this decimal, because I want to check it in a similar manner we did the previous. So what I want to do, I want to go back to the original, which is here. I'm going to go to my y equals, and I'm going to type that in. I'm going to type in just the expression. I'm going to say 1 plus 2x to the power of -3 over x, right? So now what we're saying is x is closer and closer to 0 from the left to the right, we're saying it should approach this number down here at the bottom. Okay, so I'm going to call on this function, right? And first I want to do, okay, let's start with -0.1. That's slightly to the left of 0. Okay, we get an answer. Now let's get a little bit closer to 0. Let's do -0.01. Okay, we get an answer. Now let's just keep getting a little bit closer and closer to 0. 0.001. Notice that this decimal is approaching to the decimal that we evaluated, right? 0.01, all right? So as we come from the left, so that's a confirmation, right? And we could also we can confirm it going from the right as well, right? So I'm going to stand by this result. As we get closer and closer to 0 from the left or the right, it approaches e to the -6. Okay. All right, and then I think we have another one. Let me go like this. Let me just go ahead and pull it. The other one is right here. So this is number 8. We have the limit as x goes to infinity. We got the natural log of x times 1 over x. I mean, not times, but natural log of x to the power of 1 over x. Let me take this guy and give myself some space right here. Okay. So now, with this limit, as x goes to infinity, so this exponent is going to go to 0. This goes to infinity. Infinity to the power of 0 is an indeterminate form, right? Let's see. So now we want to get this exponent to come down. So whenever we're trying to target the exponent, we might consider the whole thing, this same technique, e to the power of natural log, right? Because e and natural log are inverses of each other. They cancel each other out. So then when we take the natural log of that expression, that allows us to bring the exponent down in front, and then we can evaluate, right? So let's see this in action. These are a little bit of a doozy, so you just have to kind of take your time and just keep working, and eventually you'll get there. So now we're going to say e to the power of natural log of that thing. Right? So we have the log of the log. It's a double log going on here, right? So now again, what this allows us to do, let's see. Before I do that, okay. So then this is going to be the same as now. We can pass this limit through. This is going to be the same as e to the power of the limit as x goes to infinity of the natural log of the natural log of x to the power of 1 over x, right? So let's focus on the exponent, and we'll come back to this expression. So then if we're going to do the limit as x goes to infinity of the natural log of x to the power of 1 over x. Now, because we're taking the log, again, this allows this power to come in front. So then this is going to be equal to the limit as x goes to infinity. We're going to have 1 over x times the natural log of x, all right? So this allows us to write it as a fraction, which is what we wanted, so that we can apply L'Hopital's rule. This is going to be the log of x over x. Now we're ready to apply L'Hopital's rule. So we did have to apply some manipulations using exponents from college algebra, right? Um, you know, I didn't realize the power of college algebra. That's a basic course, or that's a foundation level course. I never took college algebra. I just knew how to do the stuff like through, I guess, high school. But my high school, there were some things in college algebra my high school never mentioned. So me trying to move forward, I wasn't playing with the complete set. I wish I had known some of the stuff from college algebra going forward. But that's the long and short of all of this. But now I know it, and like hopefully I'll just get back in the game and I get back in there after teaching it. But anyway, so now let's go ahead and apply L'Hopital's rule, right? So we're going to take the derivative of the top, take the derivative of the bottom, and move forward. So this is going to be the limit as x goes to infinity. Now, if we take the derivative of the top, the derivative of log is dx by x, right? So this is going to be d by dx of this thing over this thing, right? And then the derivative of the bottom ends up being 1, right? Or d by dx of x is 1, so I'm not going to write it just to minimize the clutter. So then, okay, so then if we take the derivative of the top, that's going to be the limit as x goes to infinity of, again, the derivative of log is dx by x. So in this case, it's going to be 1 over x. And then the natural log stays. I think we still have we have 0 divided by infinity. So let's just do L'Hopital's rule one more time. Let's do it again. So this is going to be the limit as x goes to infinity. Now, I'm going to rewrite it. Let's do this. The top, instead of doing 1 over x, I'm going to write it as x to the minus 1. And I still haven't taken the derivative yet. Now let's go ahead and let's apply L'Hopital's rule. Okay. So the top is going to become negative x to the negative 2. That's the shortcut for the power function. And the derivative of a log is 1 over x. Okay. Okay. So let me see. So now at this stage, we have the limit as x goes to infinity. I'm going to write it like this. We have this negative x to the negative 2 over x to the negative 1, all right? So now we have the same base. We can condense this into, we can like condense this or simplify it. And so when you divide the same base, we can subtract the exponents. So this is going to become the limit as x goes to infinity, negative x to the negative 2 minus a negative 1, right? That's everything written out. Ultimately, what we're going to get, the limit as x goes to infinity, that's going to be a negative 1. It's going to be negative x to the negative 1, right? So then this is going to be the limit as x goes to infinity. It's going to be negative 1 over x. Now, so then that's, as if we evaluate the limit, this is going to be negative 1 over infinity, which is essentially 0, right? So then now we need to go back and plug it in here. Let's copy and paste. So our claim is that this expression is equal to e to the 0, which is 1. Okay. Let me go style like this. And then to convince ourselves of this answer, right? Let's check. So again, I'm going to open up my calculator. Okay, I'm going to clear. Now I'm going to type the original in, which is right here. All right, I'm going to go to my y equals. Now I'm going to type the expression. We have parentheses, natural log of x. Okay, I'm going to do it like this, to the power of parentheses 1 over x. Okay, let's see, how do we do? I'm going to quit. Okay, I'm going to go to variables. I'm going to call on that function I just typed in. Now, as x goes to infinity, right? So we got an answer of 1. So as x gets really, really large, I'm going to start with 100. All right, we get something that's very promising, right? It's already close to 1. Let's go ahead and do 1,000. Even closer to 1. Let's go ahead and do 10,000. So notice as x gets really, really large, as it goes off to positive infinity, this number gets closer and closer to 1. All right. All right. So I know, I know it's a little bit all over the place, and I mean that's just the nature of it. But you saw it in action. You saw it live. Well, not really live. It's pre-recorded, but you saw it in action. Okay. So on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.